Dimensionality reduction techniques reduce the number of variables. So I'm talking about independent variables. So high dimensional data, many independent, less number of rows, less number of observations or rows, where you have less number of observations or rows. Dimensionality reduction technique or reduce the number of variables. Where we get this thing is, I have already told you the minimum sample size. In regression, the minimum sample size is minimum 20 observations per variable, and in classification, observations per variable. So when you don't have enough data in terms of observations or rows, and when you have too many independent variables, that becomes a high dimensional data. High dimensional data is data where you have more number of variables. Now, when you have high dimensional data, statistically it creates problems because the minimum sample size is not reached. Minimum sample size is not. So it violates the basic statistical assumptions of sample size. When you are looking at high dimensional data, the problem is the sample size. So for your study, you should have a minimum amount of sample size. If that sample size criteria is not met, you cannot build any algorithm. You cannot build any algorithm. So high dimensional data basically is very important when you are looking at the sample size for your model. So there has to be a minimum sample size. Without that, it creates a problem in your statistical analysis because the fundamental assumptions which we cannot violate in machine learning is the sample size requirement, whether we have enough sample or not. Take for example, let us see our data itself. There are 563 independent, or let's say 562 independent variables, 7,000 observations, and the problem a classification problem. So the problem is a classification problem. So what is the minimum sample size requirement? Sample size in observations 562 into 50, it comes to around let us say 28,100 rows. We need 28,100 observations. Technically, we need 28,100 observations, but we have only 7,000 observations in our data. This is a classic example of high dimensional data. So high dimensional data may not give you any problems in terms of accuracies and R-square and all, but the fundamental assumption of sample size, which is the minimum sample size required for a study or a algorithm or a model, gets violated. That is the problem here, dimensionality reduction. Even if you look at our Kaggle, the Kaggle house price prediction, we have 80 independent variables and 1460 observations. Of course, this is very marginally meeting the requirement. The actual observations is 80 into 1600 observation. So marginally it is creating a little bit of high dimensional problem, but not the one as severe as in the previous example. Not the one as severe as in the previous example. All right, guys, understood the context of high dimensional data?
Sir, if you run it with less observation, then will the model be underfitting then if I get the accuracy or RMSE?
That's what I'm telling
As
you.
there are more.
It will not underfit or it will not do any problem. See, most of the times it doesn't affect the accuracy or the RMS, R-square or RMSE. The only problem
More
size requirement. It doesn't affect the performance of the model as such, but the minimum sample size requirement in certain cases like clinical studies, biostatistics, pharmaceutical studies, where you need to have compulsorily minimum sample size as required. Even in banking, financial service, and insurance, the regulators have suggested the minimum size compulsion based on statistical studies for the algorithms and models. Now, the model performance will not be affected much, but it violates the basic fundamental assumption of sample size. And sampling and sample size is very, very critical in your data science projects. In your data science projects, you constantly undersample. Suppose client gave you 20 lakh rows or 30 lakh rows of data with 400 variables. You can't build a model on that, right? So what you will do? You will do a random undersampling. Use the IMBLAN package, IMBLAN library, and you randomly undersample to 1 lakh observations or less than 1 lakh observations for building the model. Once you finalize your model, you try that model on the larger data set. You can't build models on high dimensional data or large scale data. You have to constantly undersample. Undersample means reduce the sample. You have to randomly select sample that represents all the patterns and trends in the original data, and you build a machine learning algorithm and finally send it to production to implement it on a large scale. So it is not the problem with in the high dimensional data, we don't have the problem with performance. We have the problem of the fundamental assumption that a minimum sample size is required for conducting a research or a study or building a model. This minimum sample size requirement is mandatory in machine learning also, which is studies suggested by statistics. Now, dealing with high dimension data, the first one is manual selection based on the second method is to identify important variables using lasso or elastic net. There are dimensionality reduction techniques that do not delete variables, combine variables, reducing the. So you remember this dimensionality reduction techniques. They do not delete the variables. They combine the variables into components based on similarity. Based on similarity, they combine the variables into components. So once you pass the data to a dimensional reduction algorithm, the output will no longer be variables, the output will be components. And each component is a combination of multiple variables. Each component is a combination, and the most popular algorithm is the principal, also called as PCA. So PCA is a very, very popular, widely used algorithm within the dimensionality reduction technique to reduce the variables or dimensions. All right, guys, can we move forward?
Yes, sir.
All right, let us import the data which I sent you. All right, all of you imported the data. So principal component analysis is an unsupervised learning technique. There is an unsupervised learning technique. Observations correlated features into a set of uncorrelated orthogonal transformation and newly transformed principal components. So principal component analysis is an unsupervised learning technique that converts observations of correlated features into a set of linear uncorrelated features through orthogonal transformation. So this is where in orthogonal transformation, we have multiple steps. One is the calculation of eigenvector and eigenvalues. So this orthogonal transformation includes two steps, which is eigenvectors and eigenvalues, which you have to calculate. The output will be linearly uncorrelated features, and they are called as, once you have done the orthogonal transformation using the eigenvalues and eigenvectors, there will be no correlation between the components. Then the correlation between the components will become zero. Initially, when you pass the data, the input is a covariance or a correlation matrix. For the PCA algorithm is a covariance matrix. So the input is a covariance or a correlation matrix. And from this, we calculate the eigenvectors and eigenvalues, which will transform the data into through an orthogonal transformation, which we then call them as principal components. You can't refer them as. So eigenvector, if there is a square matrix M and a non-zero vector, V will be eigenvector scalar multiple of V. So scalar multiple, eigenvector. So A is a matrix, V is the eigenvector, and lambda is the eigenvalue. So this is a 2 by 2 matrix, which is simple to calculate. So for a matrix like this, -6, 3, 4, 5, an eigenvector is 1 by 4, matching the eigenvalue of 6. Based on assumption, you have to calculate. So you can use the lambda calculation, what to call eigenvalue. You have to first determine the eigenvalue. We need to find the lambda. Lambda is the eigenvalue. So using the lambda calculation, lambda using this formula, determinant of A minus lambda I is equal to 0. You get the lambda value as -7 or 6, two possible eigenvalues. Now, once you replace this eigenvalue into the vector matrix, you will get the eigenvector. So first you need to, for calculating the lambda values, you need to use the formula A minus lambda I is equal to 0. So first we need to find the eigenvalue, then we will find the eigenvector. So standardization or normalization must be done on independent variables before implementing